as we move into section 9.10, we're going to bring together some of the different ideas we've talked about thus far in the chapter, or since section 9.7. So the first theorem says if f can be represented by a power series of this form for all x in an open interval containing c, again we're talking about the radius of convergence, some interval around c, then it turns out that the coefficients here, a sub n, turn out to be the nth derivative. Remember the notation f to the n in parentheses means derivative. The nth derivative at c over m factorial, and therefore f would look like this, right? F of c plus f prime of c, x minus c. They're just filling in, expanding the sum out where a sub n is fn of c over n factorial. Now this should look familiar, right? In section 9.7, I believe, we talked about Taylor and Maclaurin polynomials. And remember, they look just like this, but it wasn't plus dot 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 at the end. You stop somewhere, okay? So that was the Taylor polynomial. So notice what this theorem is tying together stuff we did before, right? Power series and the Taylor and Maclaurin polynomials. So if you can write a function as a power series, the coefficients that you need here are the exact same coefficients we saw when we did Taylor polynomials. Right? So it's tying all that in together. So now, when we put the plus dot dot dot, this is called the Taylor series centered at C. And if C equals 0, we'll call it the Maclaurin series. Okay, so a Taylor series centered at 0 is called the Maclaurin series. Right? Remember, Taylor polynomials and Maclaurin polynomials mean you stop somewhere, right, at say n, right, of degree n. A Taylor or Maclaurin series means you keep going forever. Okay, that's the difference here. Okay? So if a function can be written as a series, a power series, the coefficients are the exact same ones that you got from the Taylor polynomial. Notice the theorem does not say that if you compute the Taylor series, it is equal to the function. Okay? Notice it says if the function can be written as a power series like this, then the coefficients have to be the derivatives here over n factorial. It doesn't say if you do the Taylor series, it is equal to f. Okay, so that's a distinction here. If it has one, it must be the form that we saw before. Let's do an example. I want you to realize the examples we're doing here, this first one is exactly what we did in the previous section when we did Taylor polynomials. We're just going to have the dot dot dot. So the example says, use the definition, this right here, to find the Taylor series centered at 0 for the function f of x is e to the 3x. So the Taylor series centered at c equals 0 is the Maclaurin series. It could have just said use the definition to find the Maclaurin series for the function. Okay, well, notice as as opposed to the Taylor polynomials, they told you where to stop. Here they didn't tell us where to stop. So we're just going to have to go blindly here. So we need f of x is e to the 3x. We need f prime. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. That's chain rule. And then the second derivative, the constant comes down. The derivative of e to the 3x is e to the 3x times 3 times the 3 already is 9 e to the 3x. Let's do one more. And the third derivative, the derivative of e to the 3x is e to the 3x times 3 times the 9 is 27 e to the 3x. Okay? Now remember what we have to do. Remember the coefficients, you plug c into the function and all the derivatives. So we're plugging 0 in here. So then f of 0, e to the 0 is 1. F prime of 0, e to the 0 is 1 times 3 is 3. Notice f double prime 0. We're just getting the coefficients here in the derivative. And f triple prime of 0 is 27. Okay, no problem. So now if we come back to our definition of the Maclaurin series, so f of x, which is e to the 3x, okay. Now what does the definition say to do? Remember it's f of 0, so 1, right, plus f prime of 0, there's your 3. And remember, this is the Maclaurin series, so it's x minus 0 to the first, or just x. And then the next one is 9. Now be careful, that's 9 over 2 factorial. If you want to think of this as over 1 factorial, I mean, that's fine. And then you're going to have an x squared. And then plus 27 over 3 factorial, x cubed plus dot, dot, dot. I mean, we could have done more. If you can't see the pattern, you might want to just do some more terms. Now, based upon this, how can we write this as in summation notation? Okay. Again, if you're trying to find a pattern, don't look at the first term. I mean, it's so simplified, it's not helpful at all. Notice in the numerator, we have a 3, a 9, and a 27. It's powers of 3. So it looks like it's 3. Notice 9 is 3 squared and 27 is n cubed. So if I put 3 to the n up there, now what are we going to have to start with n? Notice that's 3 to the first, and that's 3 squared. And so it looks like when you start with 0, right? Because that's going to be the 0 term. This will be 1. So 3 to the first, 3 to the second, 3 cubed. Okay? And then we have x to the n. Notice the power on the 3 is the same as the power on the x. So x to the n. And the denominator, we have the factorials. Yeah, notice the power on the x is the same as the factorial on the denominator. So it looks like that's n factorial. And we're going to infinity. Now, once I get a pattern based upon numbers out here, check and see if the first couple make sense, because we got the pattern from here, but you have to make sure it matches here. So when n is 0, 3 to the 0 is 1, x to the 0 is 1, and 0 factorial is 1. Here's your 1. When n is 1, I get 3x over 1 factorial. So it looks like we're okay. Okay. So it's just like we did before, but now you're trying to see what the pattern is, perhaps to write the series in summation notation. Okay, the next example says, do the same thing for sine x. F of x is sine x. Find the Maclaurin series. All right, then determine the interval of convergence. Okay, so we want to do the same thing for sine. So there's sine f prime. The derivative of sine x is cosine x. F double prime. The derivative of cosine x is negative sine x. F triple prime. The derivative of negative sine x is negative cosine x. Let me go one more. And the fourth derivative, the derivative of cosine x is negative sine x with the sine up front is, the negative up front is sine x again. Notice we're just going to keep cycling around, right? The fifth derivative will be cosine, the sixth derivative will be negative sine, etc. Okay, so we're doing the Maclaurin series, so we're plugging in 0. So f of 0, well that's sine of 0, which is 0. And then cosine of 0 is 1. And then sine of 0 again, minus sine of 0 is 0 again. And then minus cosine of 0, that's negative 1. And then the fourth derivative is 0, sine of 0 again is 0. Why don't maybe we should do one more term, because we have too many zeros here. The fifth derivative is cosine x. And so then the fifth derivative at 0 turns out to be cosine of 0 is 1 again. So I added on another term because we're only going to have two non-zero terms here. So I added another term. Okay, so now let's write the Maclaurin series for sine x. So it's f of 0, that's 0, plus 1 times x, and then plus 0 for that one, and then minus, so it's negative 1 over 3 factorial x cubed, and then plus 0, and then plus 1 over 5 factorial x to the 5th. So what's happening here, right? For the even powers of x, we have a 0 coefficient, so those are gone. For the odd powers, it's x to the 1st, x cubed, x to the 5th. And notice the denominator in your fraction is the factorial of the exponent. And notice we're alternating sign. If you ignore the zeros, it's positive 1x, negative x cubed, and then positive x to the 5th. So if you, from that pattern, you can see it's x minus 1 over, well, let me just write the cube on top. It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial minus dot dot dot. So you can see the pattern there. And we can actually write that, now that you see the pattern, we can write this as a sum I want to keep the standard notation here, right? So we can go n equals 1 to infinity. Notice all the powers are, exponents are odd. So we can write this as x to the 2n minus, 2n minus 1 over 2n minus 1 factorial, can't we? Well, okay, I haven't adjusted for the negative yet. But let's see if these make sense. So when n is 1, I get x to the first over 1 factorial. When n is 2, I get x cubed over 3 factorial. When n is 3, I get x to the 5 over 5 factorial. Notice I haven't adjusted for the plus minus, but negative 1 to the, I need the first term to be plus, so I can do n plus 1. Notice when I plug it in as 1, I get negative 1 squared, which is fine. And when n is 2, I get negative 1 cubed, which is fine. Okay, so there's our series formula for sine. So that's the first part. And then the second part says, then determine the interval of convergence. Okay. So we have our power series representation. We know how to find the interval of convergence for a power series. Remember, we just used ratio test. Okay, so I'm going to use ratio test here. So I'm going to take the limit as n goes to infinity of the absolute value. Now, I don't need the negative 1 to the n plus first term, because the absolute value will get rid of that. Now, be careful here. We're replacing n with n plus 1, so it's x to the 2 times n plus 1 quantity minus 1 over 2 times n plus 1 minus 1 factorial over x to the 2n minus 1 over 2n minus 1 factorial. Okay, let me check myself. Replace n with n plus 1, replace n with n plus 1, and then recopy my original series expression. Okay, so then I'm still going to do the... okay, let me simplify the numerator, and then I'll invert and multiply by the denominator here. So one thing at a time. So this is x to the 2n plus 2 minus 1. That's x to the 2n plus 1 over, that's the same thing down here, so 2n plus 1 factorial. And I'm going to invert and multiply, so I get 2n minus 1 factorial over x to the 2n minus 1. Okay, so that, let me check myself. 2n plus 2 minus 1 is 2n plus 1. I get a 2n plus 1 here as well. Invert and multiply, I get that and that. Okay, so now we're back to the game we were doing before. We just need to simplify. I have an x to a power divided by x to a power, so you subtract the powers. X to the 2n plus 1 minus quantity, 2n minus 1. That's 2n plus 1 minus 2n minus 1, whole quantity. So that's going to be 2, isn't it? So I just get x squared. And if I expand, which of these is the larger factorial? 2n plus 1 is larger than 2n minus 1. If you have an expression like this and you don't know which one's larger, plug in a number for n and see. Like if n is 10, this turns out to be, that's 19, and that's 21. So that's larger. So if I expand 2n plus 1 factorial, I get 2n plus 1 times 2n times 2n minus 1 factorial. So those factorials drop out, and I get 2n plus 1 times 2n. I don't really need the absolute values now because x squared is non-negative. But I didn't know that ahead of time, so that's fine. Okay, so again, if you subtract the exponents here, you'll get 2, so it's x squared. Expand the factorial, 2n plus 1 times 2n minus 1 factorial You cancel the 2n minus 1 factorials and you're just left with those first two terms. Now what happens when n goes to infinity, right? X is the variable here in my function, but in terms of the limit, n is the variable. So x you treat as a constant. So you have a constant divided by an expression that's getting larger and larger and larger. That limit turns out to be 0. And remember, in the ratio test, we were interested in the dividing line of 1, and 0 is less than 1. Okay? And notice, so no matter what x is, the limit turns out to be 0. No matter what x is, the limit turned out to be 0. So by the ratio test, this power series, x to the 2n minus 1 over 2n minus 1 factorial minus 1 to the n plus 1, converges absolutely, but converges for all x, doesn't it? So what's the interval of convergence? It's negative infinity to infinity. We did an example like this the other day for another function. We got the limit was 0, which means the interval of convergence was negative infinity to infinity. Okay. Now there's one little technicality here we have to think about. I'm going to use the sine example again. Okay, so remember in the theorem it said, if you can write a function as a power series, the coefficients have to be the same ones we found when we did the Taylor polynomials. Okay? But it doesn't say if you compute the polynomial, it actually is equal to the function. Okay? If you can write a function as a power series, the coefficients are the same ones we did with the Taylor polynomials. But if you just have a function and you compute the Taylor series from it, it doesn't mean that they're actually equal to each other. So the next theorem says, how do you know that the series that you compute is actually the same as the function you use to get it? Okay? And that's what theorem 923 says. It says if the limit as n goes to infinity of the remainder term is 0 for all x in the interval I, remember that's the interval I that's around C, then the Taylor series for f converges and equals f. And you don't need to know this theorem, I'm just doing it to show you that, how do you address that issue? If you have a function and you compute the Taylor series for it, how do you know it actually is equal to the function you started with? Because it may not be. So that's the condition. If you take the limit of the remainder terms, they have to go to 0. And so remember the Rn, okay, we're going to put the absolute value on it. That was the n plus first derivative at some value z divided by n plus 1 factorial times x minus c to the n plus 1. Remember that was the remainder term in the Taylor's theorem. So remember the remainder term is equal to this expression for some z between x and c. But the problem was, how do you know what z is? You don't know how to find the z. Okay. Well, let's do the game we always do. Let's find the biggest this could be. Again, I'm using it for the sign here. Okay. All right. So okay. So we have the n plus 1 factorial. That's n plus 1. Okay. Now remember, in this problem, c was 0, right? I'm referring to the problem we just did, right? It was a Maclaurin, so we're just going to get absolute value of x to the n plus 1. So I just took the absolute values around that part. I don't need absolute values here because n plus 1 factorial is always positive, right? So I just recopied that. C is 0, right? But x could be negative here, so I need the absolute values on that. Now notice I changed it from equals to less than or equal to. What's the biggest this is ever going to be, okay? For any z between x and c, again here c is 0, so between 0 and x, what's the biggest this can be? Now remember, I had the derivatives here. The derivative of sine was cosine, the derivative of cosine was negative sine, etc. Every single one of those was either sine, cosine, negative sine, or negative cosine. What's the biggest the absolute value of that's going to ever be for any number z, not just z between x, 0 and x. Right? If you take sine of anything, or cosine of anything, or negative sine of anything, or negative cosine of anything, the absolute value, the biggest that's ever going to be, is 1, isn't it? Right? So I can replace this term. The biggest this could be is 1. Okay? And now when n goes to infinity, let me see. Right. So when n goes to infinity, right, the limit of this is 0. And therefore the limit of that, so the limit as n goes to infinity of Rn is going to be less than that limit. Of absolute value of x to the n plus 1. And when n goes to infinity, I mean, the factorial is going to grow faster than that. Remember, x is some fixed number, and that does turn out to be 0. Okay. So by the theorem, we just showed the limit of the Rn term for this example 0, so these two are actually equal. Again, I'm not that concerned about problems of this type. I may have assigned one in the homework just so you can look at it, but I'm not really concerned that you know how to apply this theorem. Because if we compute a Taylor series for a function, if it's not equal to that, it's completely useless and there's no point in doing anything with it. Right? So all the ones we're using here are going to, when you do the Taylor series or the Maclaurin series, it's actually going to equal the function you start with. Otherwise, there's no point. I just wanted to show you there is a little technicality there. Okay. Now at the bottom there, I mean, there's a whole table on page 674 of power series. So you don't have to memorize those. These are the 4 I want you to memorize. Okay. So we already did the one for sine x. Let me write that again. So sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus da da da. Okay? Now you should remember from pre-cal, sine is an odd function. So it shouldn't surprise you that you have all the odd powers. Okay? So you're going to, again, if you want, you can think of that as x to the 1 over 1 factorial to fit the pattern. Okay? So it's all the odd powers of x, the denominators or the factorials that match the exponents, and you alternate plus minus plus minus plus minus. Okay? There's sine. Now cosine is the same sort of idea. You should know that cosine is an even function. Okay? So since cosine is an even function, you're going to have all the even powers. Now be careful. You have to start with 1. Okay? So it's exact same idea. Okay? It's exact same idea. Right? You have all the even powers. The power in the numerator matches the factorial in the denominator. And you alternate plus minus plus minus plus minus. Now be careful. A common mistake, which I will do, I will forget to put the 1. But you know you need the 1 there. Think of the 1 as x to the 0 over 0 factorial, right? That's 1. All right? If we interpret 0 to the 0 as 1, even though it's undefined. Right? But how do you know you have to start with 1? When you plug 0 in here, cosine of 0 is 1. So if you don't have that there, you're going to have cosine of 0 is 0, which is not true. When you plug 0 over here, you would get 0. So you know you need the 1. Right? So sine and cosine have the same flavor. It's x to the odd powers divided by the odd power factorial, x to the even powers divided by the even power factorial, and they start with plus minus plus minus. Okay? And then the third one here, e to the x. E to the x, you have all the odds and all the evens, and everything's a plus. Right? So it's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Okay? So it's like a combo of the two. You add all those together, but ignore the minus signs. So there's your e to the x. Oh, notice the intervals of convergence there. For all 3 of these, the interval of convergence is negative infinity to infinity. Okay? So make sure you know the intervals of convergence too. And then the last one I want you to learn is natural log of x. Now notice on the very, very right, I have the interval of convergence is 0, 2. So not including 0 and including 2. It makes sense to not include 0 because log of 0 is undefined. Right? Now, so notice the center of this is 1. So we're centering this at 1. So therefore the terms have an x minus 1. So it's x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3 minus x minus 1 to the 4th over 4, etc. Okay. Notice this one alternates plus minus as well. So e to the x is the only one of these 4 that doesn't alternate. It's x to the minus 1 first. If you want to think of that as over 1, right? So notice the power in the numerator, the power of the x minus 1 matches the number in the denominator. But what's the big difference here? There are no factorials. For sine, cosine, e to the x, they're all factorials. For natural log, they're not. Okay, be careful. But it does alternate, plus, minus, plus, minus. And you have to remember, even though it says natural log of x, we're centering at 1, x minus 1. Now, it makes sense. You can't center log, if you try to center log x at 0, you can't go to the left because you can't take log of negative numbers. So it makes sense to shift it over. I mean, the 1 isn't special. We could have shifted over, to 6 or something. Right? So we're going from 0 to 2, we're centered at 1. So the radius of convergence of this power series is 1. Because we're centered at 1 and we're going to 2 or 0 either way. Okay, so those are the 4 I want you to know. Okay, so I want to just do one more example here in the video, and then the rest we'll do in class. So this next one says, use the table of power series for elementary functions. That's that table I mentioned on page 674. To find the Maclaurin series for the following function, g of x is 2 sine of x cubed. So again, they don't want us to do this from scratch, right? We could take a bunch of derivatives, and it said Maclaurin. Take a bunch of derivatives, plug in 0, and find the power series, just like I did in the previous examples. That's not what they want us to do here. Right? They want us to use one we already know. Right? So in particular, let's start with sine x. So that's the one we know. That's x. Remember, it's odd powers. Minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, etc. Okay, so think of that as your parent function. So I want to construct the function g from the function sine x. Well, what could you do? Well, I don't want an x, I want an x cubed. So what do you do to this function to get sine of x cubed? Substitute x cubed for x. So sine of x cubed, right? So I just substitute x cubed for x. So I get x cubed minus x cubed cubed over 3 factorial plus x cubed to the 5th over 5 factorial minus x cubed to the 7th over 7 factorial. So if we want to simplify, that's x cubed. Again, you can think of that as over 1 factorial if you want. Minus x to the 9th over 3 factorial plus x to the 15th over 5 factorial minus x to the 21st over 7 factorial. This is just algebra. And now all we need now is the 2. So to get g, what do we do to this function we just created? You just multiply by 2. So it's just 2x cubed over 1 factorial minus 2x to the 9th over 3 factorial plus 2x to the 15th over 5 factorial minus 2x to the 21st over 7 factorial. So there's your power series for g. So start with one you already know, and we're doing transformational stuff. So substitute for x and then multiply by 2. I could have multiplied by 2 first and then substitute for x. I would have gotten the same thing. Now, how do you write this? If we wanted to write this as a summation, okay, how would we do that? Well, we have a 2. That's no problem. And what's the relationship between the factorial in the denominator, right, and the power here? Notice the exponent on the x is 3 times the factorial in the denominator. Notice all the denominators here are odd. So you can write that as say 2n minus 1 factorial. Remember, 2n plus 1 and 2n minus 1 is always odd. Right? So if I write that as 2n minus 1, and now what's the exponent going to be on the x? So I have an x to the, it's 3 times the expression for the factorial. So it's 2n minus 1 times 3, which is 6n minus 3. Or again, 3 times the quantity 2n minus 1, however you want to do it. And notice that it's also alternating, so I have to adjust for that. So I negative 1 to the, now it depends on what I'm starting with. Yeah, let's figure that out first. So if I try, notice if I can't start with 0 because that'll give me a negative 1 factorial. Looks like I need to start at 1, doesn't it? N equals 1 to infinity. Because when n is 1, I'll get a 3. And I'll get a 3 up here, and I'll get a 1 here, which is what I want. And so with that in mind, I need to start with a positive, so this needs to be n plus 1. Because when I plug a 1 in here, it'll be negative 1 squared, and that's positive. Okay, so there's that example. That's creating a power series for a function we don't know from a function whose power series we do know.